Okay, so class, today we're going to talk about plate tectonics, and I'm going to let you know what you need to know. Okay, this is pretty easy stuff. It's fun stuff, though. So, how does the theory of plate tectonics influence the way the Earth is today? So, we've talked about plate tectonics a little bit before, and how it impacts the Earth, and how the Earth is, relying on plate tectonics for its creation, and how the organisms have evolved based on how things move around. So, plate tectonics and the theory of plate tectonics. So the surface of the Earth is composed of about a dozen major rigid moving crustal plates and several smaller plates. So you have like the really big plates like the North American plate or the Atlantic plate, and then you've got like little small ones like the Juan de Fuca plate and stuff like that. And all these interactions, each one of them's different. Each interaction is different, and they keep moving around and crashing into each other, and their movements change how the Earth is and how it forms. So here's the map of. I'm gonna let all the stuff move around. Here's the map of the major plates. So you've got things like the North America plate over here, a really big plate, and you've got a little small plate like the Caribbean plate or the Cocos plate. And you've got the Pacific plate, which is massive. So this massive Pacific plate has all of these rough interactions, and this is what is called the Ring of Fire. So you've got all the world is pushing into these plates, and that's why you have so many volcanoes and earthquakes and things like that along that Pacific plate. And you can see how the Earth is formed, and these plates sit on top of the mantle. Okay? So you've got your plates. These are slabs of the Earth's lithosphere, or crust and upper mantle. Average thickness, about 100 kilometers or 62 miles. So, that's pretty thick, but in comparison it's really not that thick. So you've got things like the crustal plates are like 62 miles thick, whereas you have like the oceanic plates are only about 4 miles thick. So and most of these plates, they support continental drift. So continental drift states that the continents are drifted and still are drifting apart. So these continue to move around, and you've got your mid-oceanic ridge that goes all the way along the middle of Atlantic. Okay, this one moves and separates, and that's where the entire Earth moves around these two plates. So it separates. It's just like this. I'm going to show you guys a little picture later. It separates along that mid-ocean ridge in the Atlantic. It's about a 2,000-mile mountain range. It goes right down the middle of the Atlantic. Okay, all these plates are moving around. It's really cool how they figure this out. So this is kind of an older map to show how these plates have moved around over time. So, it's not a real fast process. This has taken millions and millions of years for these plates to move inches at a time. Okay, so you got this upper one up here. This is your Pangea, where all the plates are kind of together. Was one massive supercontinent with a whole bunch of oceans surrounding everything. Okay, and then you've got your differentiation. So it's starting to spread apart. You see this? There's this little gap here. This little gap. So why do these plates move? Well, due to the tremendous heat. So much heat caused by these frictions. Rocks in the asthenosphere it's like hot taffy, so it's very, very viscous and it moves along it. So this allows plates to ride on top of this hot flowing rock. So you got this lower plate here, this upper plate here, and it just kind of slides along because of how the asthenosphere is. Okay, the plates move because heat is being released from deep inside the Earth, so you have all this heat coming up from the mantle that's driving up through these cracks. And up through these cracks, all this heat heats up the rock and melts it and allows it to move. So, heats it up and moves, heats it up and moves. And that's how everything keeps moving around. And these convection currents, is what causes this hot movement. Okay? So basically all these little broken little pieces in the Earth are what allows this heat to escape. So here's kind of events at the plate boundary map. So you've got all these little plates here. You see all the little jagged ridges, and this is how the plates are active, and see what happens. Oceanic crust, you've got your oceanic ridge where your seafloor's spreading. You've got your subduction zone where the plates interact and the one moves underneath. And when it moves underneath, it lifts up mountains and also can lift up magma, creating volcanoes. So that's your subduction zone. Okay? So here's a interactive display here to show that. So you've got, here's a divergent boundary. Okay? Just like I showed before, that magma comes up from underneath in the mid-ocean ridge right down the middle of the Atlantic and spreads, slowly creating oceanic floor. And this has been happening for millions and millions of years, slowly creating oceanic floor. Now you've got a convergent boundary. Okay? This is where two plates butt up against each other. You've got one plate that's like this and one plate like this. If one is stronger than the other, or if this is an oceanic plate, it's got more water vapor. So this one goes underneath it, and this heats up, it gets superheated gas. And what creates a lot of your volcanoes and things like that, and geysers, is when these two plates interact, one is going to go under the other. And usually it's the smaller plate that goes under. So like your Sierra Nevada mountains, that plate's gone because it completely subducted and is gone. Or you have like Mount St. Helens up north, that's on the Juan de Fuca plate, so it's still there. So it's slowly transducting. Here you've got the transform boundary. Okay? This is what, you get a lot of earthquakes from this. This is a strike slip fault here. So things are, going along here side to side. And this causes a lot of earthquakes because you've got a lot of friction, okay? So your lithosphere, asthenosphere, you got all this friction going back and forth. Okay, it causes a lot of earthquakes. So this is like the San Andreas fault. So you've got like Southern California here, or this is right by San Francisco Bay, where you've got San Francisco on the right and the ocean on the left, and they are going strike slip past each other. Okay, so this is the San Andreas fault. Here's a plate inclination. Okay, here's all of them working at once. Okay, so you've got those mid-ocean ridges separating like this and creating more oceanic floor. Those crustal plates run into other plates and cause volcanoes to move. And all this happens from all this rising magma that's coming out and all that heat and convection currents that are made move all around the world and cause our volcanoes. Okay. Alright, so, this has been happening for millions and millions of years, okay? You've got your Permian period, you've got your Triassic period, here's your Gondwana land and your Laurasia. There's your Pangaea, the original supercontinent. And slowly you can see over time, these have started to separate into what looks like it is today. And there's been a lot of different ways to tell how this happens, okay? You've got like things like the fossil record that can show when things started to move around. You have, things like different rock formations that can, and all kinds of other methods to show exactly when these things moved, including like, you've got these little magnetic rocks, and based on where they are and where they're laid in layers, you can see, where these rocks were, because they'll orient to the North Pole. So you'll have one layer of rock that may be facing this way, and then you'll have another layer of rock that's maybe facing this way. And that's happening because these plates are moving around the Earth, and they're changing their, so that's another way to tell. It's pretty cool. Okay, so here's, just like I talked about the fossil record, so here's where all those continents were together, okay? And you've got these bands of fossils that link the continents together, okay? So you got your fossil remains of your Triassic land reptiles, when South America and Africa were real close together. Because if you ever look at a map, South America and Africa, they look like a puzzle piece, and we'll talk about that in a second. We've also got Antarctica and India when they were all together. You've got these bands of fossils that link the two continents together Because then after that in the fossil record, there wasn't shared species. So you even have a plant here. This plant, it goes through all of them. Isn't that crazy how that works? And then after that, you didn't see that stuff anymore. So this is a really good example of how all these plates work. So here's this guy, Alfred Wegener. Pretty funny old British guy looking guy with a pipe here. So he proposed that in the distance past, the Earth's continents were all joined as a single landmass. Okay, so he looked at a map and saw that, like I was saying, like South America and Africa looked like they were really close together. So that's what he said. He thought they would fit remarkably well in a map, and it got him thinking. And if the Americas were moved around next to Africa and Europe, there would be a match of ancient continental rocks and tectonic fold structures. So he saw that, based on how the maps were going, maybe this was here. So then they went through and they looked at the rocks and they looked at the fossils. And with Pangea, he placed all the continents together like a puzzle, and it formed that large landmass called Pangea, and it was accurate. Everything matched up, and it was good. So here's a little game you guys can play later, okay? It's a little Who Wants to Be a Millionaire? Here, and we can play this real quick. So, on what type of evidence was not used by Alfred Wegener to support his continental drift thesis? So did they use evidence from fossils? Yeah, I just talked about evidence from fossils. Evidence from climate? Maybe it could be evidence from climate. What about landforms? Definitely from landforms, because we talked about that geology. So, evidence from human remains? No, I don't think humans have been around long enough. The Earth's been around for a long time. So we're going to go with evidence from human... Oh, hey, I won $200. Okay, let's go to the next one. Let's do one more. I could barely read that. That shapes the Earth's surface with buildup of mountains and land masses are called... constructive forces, destructive forces. I'm going to go ahead and get a hint on this one. The answer is not C. Okay. So, temperature and pressure, destructive forces, seismic sway. I still don't know. What do you think? Okay, you guys are being quiet. What do you think?
I think it might be the temperature and pressure.
Temperature and pressure. Oh, no. Okay, well, you guys can play at home. There's lots of questions, okay? We can play later. Okay? So now we're going to go to our worksheet. Okay. So, set this up here. All right. Yeah, you got a question?
I didn't get the answer watching the PowerPoint of number 2. What kind of movement results in volcanoes?
We'll go through that in just a second, okay?
Okay.
Because I gotta let the rest of the class go through it. So we're gonna go through the questions first, okay? So who was the discoverer of plate tectonics? Number 2, what kind of fault movements results in those volcanoes? What was the supercontinent called? And where was the video clip filmed? Okay, so you guys go ahead and work on that. So what was your question again, Nico?
My question was number 2. What kind of fault movement results in volcanoes? Because I didn't really read that.
Well, it's the subduction zone is where that fault movement happens.
Oh, okay. So I think I put down this subduction zone.
Yeah. And you understand what this word means, right? Supercontinent?
Yeah, isn't that the big cookie thing?
Yeah, that's a big cookie. Okay. Alright. You guys keep working on this. Just look up at me when you guys are all done, okay? Okay, so who was the discoverer of plate tectonics? Yeah, Nico.
I think it was Alfred. What was his last name?
It's Wegener.
Okay, Wegener.
Okay.
Sorry, it's kind of hard to pronounce.
Okay. And so, subduction zone is going to be number 2. I took that slide out. Sorry about that. That was a little bit confusing there. So sorry about that. So 2 is a freebie for you guys.
Yay.
And so the supercontinent, that's yeah, Angie.
Pangea?
Pangea. That's right. And okay, and I didn't get to that video film, so I'm going to show you guys that in a second. Okay. So let's go look at that video film.